Hello everyone, I'm Elena Agostini from NVIDIA, and today I will present to you how we use the DPDK framework to implement our Aerial 5G software. So this is an overview about what a 5G network is, very high-level components. And I just wanted to, let's say, clarify that I'm going to focus on the left side of the picture, so the G0B, and specifically the interaction between the distributed unit within the G0B with the radio units connected to the wireless clients. While in the next session, my colleague Gal, he's going to focus mostly on the right side of the picture, so on the UPF functionalities and how they can be combined with DPDK. Okay, so let's focus on the left part. Aerial 5G is a software that we implemented at NVIDIA, and basically it is responsible for the physical layer within the distributed unit within the G0B. So it means that we can run signal processing, we can accelerate the signal processing entirely on the GPU. On top of that, what we can also do is, well, what we need to do because of where we want to place the aerial software, so at the physical layer of the DU, we also need to take care of the communication with the radio units connected to the wireless clients. And this has to happen in a very specific way following the eCPRI protocol over the front haul. The front haul is kind of the interface, the name of the interface between the DU and the radio unit. And we need to do this communication according to specific time boundaries. And we also need to exercise inline packet processing because when we receive packets from the radio units, we need to process the packets as soon as they come into the GPU. So before digging into the details, I wanted to present to you the software and hardware stack that you need to have on your system to run the aerial software. Starting from the bottom layer, that's the hardware part. So you need to have basically, of course, a GPU and a network card on your system, and they must be connected through a direct PCI connection. It means that you need a PCI bridge that creates, again, a direct connection, so not through the host bridge of your system, between the network card and the GPU in order to enable the maximum throughput in the communication between the GPU and the network card. The motivation for this kind of topology is because in this way you can maximize the throughput when you're doing GPUDirect RDMA. That is a well-known technique that allows basically a network card to send and receive packets directly using the GPU memory without doing CPU memory staging copies, or there's no intervention at all of the CPU. So that's the motivation for, let's say, the hardware topology. On top of the hardware topology, of course, you need to have also drivers. Of course, the NVIDIA driver and the MOFED in order to make the GPU and the network card usable. But then you need also to run the NVIDIA Pyramid module. That is a kernel module that you can find in the NVIDIA toolkit. And this connects, basically creates the bridge at software level between the network card and the GPU. So the NIC can fetch the data directly from the GPU memory, for example. You need also the GPUDirect kernel module. That is another module that allows you to basically enable a direct communication between the CPU and the GPU, because you can allocate memory on the GPU, map it with GPUDrive, and then you can directly access it from the CPU as it was another CPU memory location. And finally, there's also the need of these two kernel modules, PHC2Cs and PTP4L, that are more time-related. And of course, PTP4L is to be synchronized with respect to time with other components in the network. But also PHC2Cs is there because for the reasons that I will explain in a moment. Basically, you need to have the clock within the network card synchronized with the clock of your system. So a timestamp for your CPU is the same timestamp for your network card, basically. Means the same thing. On top of the drivers, we have the libraries. Of course, we have the CUDA library, and then we have DPDK. And specifically for DPDK, we needed to use these three libraries, modules, features that are the GPUDev library. That is a library that creates all the connection between the GPU and the network card, or the GPU and the CPU. So you can allocate, for example, a DPDK mempool in GPU memory to enable GPUDirect RDMA, or you can do the trick of direct access of the CPU to the GPU memory through the GPUDev library, which in turn uses the GDR driver module. So for these kind of reasons, we need the GPUDev library. Then we need, of course, a combination of DPDK ATHDev and DPDK flow. And the reason is because Aerial needs to receive or send packets, so you need ATHDevs to create queues. but also needs to use flow steering rules on the receive side if you want to receive a specific type of traffic in a specific queue. So you can kind of speed up the packet processing because you precisely know in that queue which kind of packet you will find. On top of all of this, of course, we have the aerial application that, as I said, is running GPU signal processing, and this is totally, built on top of CUDA, of course, it's not network related. And then there are network related stuff like GPUDirect RDMA, as I said, eCPRI, in-cap or decap, means that if you have to communicate with radio units over the frontal, you need to follow the eCPRI standard protocol. So at application level, you need to understand what is an eCPRI header, how it works, what does it mean, and so on. We want to have PHC2Cs running on the system, and this is also the reason for which we wanted to use DPDK. Because accuracy and scheduling, or time at send, it has different names basically, is a way to send the packet in the future. So in the present, you prepare the packet, you assign a timestamp in the future, and push the packet through the MBUF into the network, into the send queue. What will happen is that the network card later will take care of sending the packet at the right time, mostly managed at a hardware level, and so you don't have to worry about firing the packet out into the network at the right time at software level, because the network card will take care of it. So that's a very nice feature that we really need in mobile networks. And then, yeah, as I said, Ethernet stuff, eCPRI flow recognition, and CPU to GPU interaction. So let's look at the kind of data flow that you can find in aerial, well, you can find in the physical layer of a G0B in the DU side. You can receive packets from the wireless clients, where the U is, or you can send packets to them. If you're receiving packets to them, it means that you are during an uplink slot. A time slot is basically typically 500 micro time window, where you are receiving, in this case, in uplink, packets from the UEs in a specific way. So if the network, let's say, the 5G network wants to start an uplink slot, basically the CU, still within the G0B, forwards to the DU a request to start an uplink slot. As soon as the DU receives this information, it provides this information to the lower layer, so L2 plus, and then finally layer 1, where it's the physical layer, and where we found aerial. And then two things happen here. So the first one is that aerial prepares with CPU, using CPU memory, regular DPDK communication pattern, creates packet on the control plane and send them to the radio unit, saying, hey, I'm about to ask you to receive data from the UEs, please send them to me on the U plane. So the radio unit is ready, knows what to do, so it listens through the wireless medium data coming from the UEs, and then basically encapsulate those data on basically Ethernet packets using the eCPRI protocol. What happens is, basically, as soon as these packets are received by the aerial software, the packets are basically received directly in the memory of the GPU. So as soon as they are coming in, the GPU can immediately start to process them. So that's why we say that also aerial does inline packet processing, because as soon as packets are coming into the memory of our software, they are immediately processed. And then the final result of this overall signal processing calculation is then forwarded up to the upper layer, and then the TCU has a response for the uplink request. So for, let's say, the goal of this session, I would like to kind of zoom in the uplink, specifically to understand how the PDK can be used in an uplink slot to receive and process data packets. There are a lot of, let's say, components in this picture. I will try to drive you through all of this. So let's start from the left side of the picture, where there are UEs. UEs are sending data to the radio units. The radio unit basically encapsulates this data into Ethernet packets, having, let's say, a structure like the one in the picture. So an Ethernet header, eCPRI header, and then the actual payload of the packet, which holds UE's information. Packets are sent over the network to the aerial software, where there are multiple receive queues. Receive queues created with DPDK in combination combining ATH-dev and flow in order to precisely understand from which radio unit packets are coming, which kind of eCPRI attributes those packets have, and so on. And if we attach to these queues a DPDK GPUDev mempool, so a mempool created in GPU memory, basically you have for free a DPDK level GPUDirect RDMA. So packets are directly coming into the GPU network, GPU memory, sorry. A DPDK GPUDev mempool has a shape like this one here. And basically it's kind of a regular DPDK where the MBUF headers are in CPU memory. So the CPU can manage the receive queue, receive packets, get packet information, and so on. But the actual payload of the MBUF, it's an offset, let's say an address, in a GPU memory location. So basically, a DPDK GPUDev mempool is using the external MBUF feature that we know that DPDK exposes. So steps are, number one, the CPU thread invoke the DPDK receive function to receive packets from the queues. And the packets, as I said, are flowing directly into the GPU memory. So once the CPU thread receives a subset of the overall packets of this time slot, it has to notify the GPU that a new bunch of packets is ready in GPU memory and they are ready to be processed. And to do that, it uses another object that you can find in the GPUDev library, that is the communication list. That is basically a list of structures allocated in a memory that is shared between the CPU and the GPU, so they can both read or write this, let's say, the list, the memory structures in this list. So what happens is the CPU thread populates the next item of this list with MBUF information, so which MBUFs can be used to receive packets, packets addresses, number of packets, and so on. On the other side, so on the GPU, specifically for the NVIDIA GPU on the CUDA stream, you have what we call the eCPRI reorder kernel. That is a CUDA kernel responsible to wait for new packets, so an update coming from the CPU, and as soon as it detects this update, it basically reorders the received packets. Means that in a parallel way, of course, because we are on a GPU, basically it looks at all the received packets, and for each packet, it tries to detect information from the header, Ethernet header, eCPRI header, and basically it tries to understand in which offset of the uplink input buffer the payload of that packet should be copied. This is why, because, the reason for which is because we cannot start signal processing in an uplink slot if we don't rebuild the original frame coming from the UE client. So what we need to do is a kind of a pre-processing stage where packets are reordered in a contiguous buffer of GPU memory, and so the signal processing can start. But we can say that this is an inline GPU inline packet processing because CPU and GPU are working together in parallel. As soon as packets are coming in, the CPU notifies the GPU processes them, while the CPU is receiving other packets. So at the end of this process, at the end of the 500 micro, that's the time slot, packets are reordered in an uplink input buffer, and so the signal processing can start. After that, the signal processing is done. There's a tiny CUDA kernel on the same stream at the end that says, hey, I'm done, and it updates a flag in GPU memory to notify the CPU about it. And this memory flag has been basically allocated through the GPUDev library in a GPU memory location visible from the CPU, mapping it with GDR driver. And so in this way, the CPU can say, OK, the GPU ended the signal processing. We have the output. We can push the output to the upper layers to reply to the uplink request. If we want to send, so the send side, let's say, of the problem, then we are in the downlink time slot, still a time window of 500 micro, where the physical layer has to send data to the radio units, and then in turn, the radio units must forward those packets to the UEs. So the procedure is kind of the same. From the CU, the DU receives a downlink request. It pushes this request to the all the layers in the DU up to the bottom layer. That's the physical layer. And here, something similar as the uplink slot happens. So still control packets are sent to the radio unit to give instructions about the fact that you're about to send data packets that must be forwarded to UEs. And then the GPU starts the signal processing. The output of the signal processing is split into multiple Ethernet packets. And then the result is sent on the U plane, I mean to the radio units. And the radio unit will forward those packets to the UEs. And even in downlink, DPDK is useful to implement this algorithm because, well, at the initial stage of the downlink time slot, the GPU and the CPU are really working in parallel because the GPU immediately starts the signal processing to produce the data that must be sent over the network, while the CPU can prepare packets in terms of headers, offsets, and so on, so to be prepared as soon as the GPU completes the signal processing. Specifically, in this case, we need to have two DPDK mempools. One DPDK mempool with regular CPU memory, and the second one in GPU memory allocated with GPUDev. So what happens? While the GPU is processing, well, is doing the signal processing, the CPU is populating, is using the mbuffs of the first DPDK mempool in CPU memory to put the packet header into the mbuff payload. So Ethernet header and eCPRI header, basically. Next step is to prepare the packet payload. So the packet payload must be fetched from the GPU. So what happens is the CPU redirect the mbuff payload of the mbuffs in the DPDK GPUDev mempool to the right offset of the downlink output buffer. So they will refer to a memory location in GPU memory, a memory address in GPU memory. And in this way, the final effect is that we're gonna send packets, half of the packet, let's say, fetched from the CPU memory for the header, and the remaining part of the packet fetched from the GPU for the packet payload. Another thing that's happening here is that the CPU prepares the timestamps for the mbuffs. So basically, to implement the specific timed send pattern that we need to respect in 5G networks, we need to send packets at the right time. So we can do that basically using the accurate send scheduling feature I presented at the beginning. So from the CPU has associated a timestamp in the future to some of the mbuffs in order to send the packet in the right way. I will show you in a moment what does it mean. And then basically the CPU waits for the completion of the signal processing, still, let's say, notified through the shared memory between GPU and CPU. And finally, the CPU fires the packet on the send queues. On the right side of the picture, you can see what is the final effect of all this preparation. Basically, in 5G networks, you cannot just create and send packets over the network. As I said, you need to respect a timed pattern. And so in a slot of 500 macro, you have 14 symbols to send your packets. And each symbol is basically composed by 36 microseconds from a time point of view. So each symbol will send, during each symbol, the aerial software will send a subset of the packets that we must send during the slot using the accurate send scheduling feature, so at the right time. And as I said, the final packet will be fetched by the network card from two different places, the header from the CPU memory and the payload from the GPU memory. So this accurate send scheduling feature may not be a well-known feature. I mean, personally, I don't know a lot of applications actually using it. I dumped here a super simple recipe, super high level. But if you want to play with it, you can use testpmd, the tx-only file, .c source file. You can find the implementation. And of course, the assumption is that PHC2C is running on your system. So the clock on the network card and the clock on the system, they basically speak the same language. And of course, if you want to use this feature, it's your responsibility, so application responsibility to enqueue packets in the right order. Otherwise, you may not have the desired effect if you mismatch with the timestamps and timestamps order. So This is my last slide. I just wanted to give you some references about other sessions or blog posts where I discuss about these kind of technologies. We presented the first idea of Aerial at the GTC, but there's also an interesting NVIDIA blog post where you can see specifically how the DPDK GPUDev library can be used not only in Aerial, but also in other use cases. Interesting to note that we submitted a paper, has been accepted to the EE about this Aerial plus DPDK effort. And if you want to learn more about this GPUDev library, you can go into the DPDK documentation and you will find all the details. And that's it. Thank you.
I'd like to ask a question. How many CPU and combined with how many GPU will reach the perfect performance?
That's an interesting question. So let's say that we were able to manage 4 radio units with 1 CPU core and 1 GPU. And if you want more capacity in your system, the GPU can remain the same. It can be an A100, for example, if you are asking for also the type of GPU. But if you want more power on the system, you just need to add another CPU thread that will receive packets from another subset of radio units, basically. So it's kind of a direct function between how many radio units you want to support with a single CPU thread to forward the packet information to the GPU and so on.
Yeah, okay. And if we choose 1 CPU and plus 2 or 4 GPU, and if the data is transferred between the GPU, can we use NCCL, NICO, and combined with DPDK? Yeah, they can act at different layers, like you can use the DPDK on the network side just to receive packets in 1 or multiple GPUs, and then once the data lands on the GPU, you want to use NICO or other protocols to basically share the data across the GPUs. That definitely is doable. Yes, yes, yes. Okay, thank you.
Thank you.
So with architectures like Grace Hopper, where you have the CPU and the GPUs, which are more tightly integrated, do you see any optimizations in terms of how the memory pools are created? Right now, I see that you have got memory pools for GPU, memory pools on the CPU, but can that be optimized into creating a single memory pool for both CPU and GPUs?
So yes, it's like, so you can, the nice thing is that, yeah, the interconnect between the CPU and GPU in Grace Hopper has been really improved. So the throughput in the communication is high. And so it's also increased the, let's say if you have a CUDA kernel that want to access the memory of the CPU, this can be done at a very high throughput with respect to other systems. So if you want to have a single DPDK mempool accessed by both GPU and CPU, I would suggest to put this DPDK mempool in CPU memory because, again, the throughput, I mean, also the latency of CUDA kernels accessing the CPU memory has been really improved. But, of course, it depends from case to case. For now, still in Grace Hopper, the 2 memories remain, from a hardware point of view, separated, even if they accelerated the access.
Okay, so even on Grace Hopper, you see that there would be these 2 memory pools still existing?
Well, not additionally. It's like if you create a DPDK mempool in CPU memory, like this one, right? This can be also accessed by the GPU in a faster way rather than a normal, x86 system. So you can have a pretty decent access, let's say, latency for CPU memory. So just if you want to have just 1 DPDK mempool. Of course, if you separate them, it's always better because a CUDA kernel has the lowest latency possible you can get running a GPU workload is to have data located in GPU memory. But yeah, I mean, I hope this answered your question.
Yeah, okay. It did. Yeah, I thought we made such an advancement that we can have everything in one memory, but looks like we still could keep.
Yeah, they are still separated anyway.
Thanks, a very interesting presentation. So, does the GPU keeps on polling for new work, or can you bring it to some sleep state and consume less power when there's no work to do?
Well, it's up to you. So let me bring, okay, this is the slide, right, where the GPU is polling, waiting for new packets, right? That poll box in the CUDA kernel, it's something that the application implements. So you can decide, you can have an infinite while loop while a certain condition happens, and so you are constantly polling, or you can decide to poll after, I don't know, a bunch of microseconds. It really depends on your application, and you decide. The DPDK part is to enable this mechanism and connect the GPU and the network card. But then everything you see here, it's pure CUDA code and application code. So again, you decide how frequently you want to poll the memory.
Thanks.
Okay, I have one question. So let's imagine I'm using a GPU from NVIDIA and a networking card from AMD. Am I able to forward the data directly to the GPU from the AMD networking card?
It depends if let's say the AMD card can map the GPU memory at driver level, right? So here we are using the MLX5 driver, which refers to the NVIDIA network card. If AMD is able to write a kind of a similar driver, but with their hardware, and so they can map as the NVIDIA network card is doing the GPU memory, yes, there's no hardware limitation in that. It's more.
And for the opposite, if I'm using an NVIDIA networking card with an AMD GPU?
That's another interesting question. And I can kind of answer the same, like the GPU driver we have in DPDK has been implemented with the CUDA driver to support NVIDIA GPUs. But if AMD want to chime in and write their own driver, they can definitely do that. Yeah. I think that AMD has something similar, but I never worked with that. But from a DPDK point of view, it's totally doable if they implement the right driver.
Yeah. My last question is, did you hear about any other GPU vendor writing some GPU driver in DPDK?
No.
You are not aware?
I mean, no, I'm not aware.
So that's a call for action.
If someone wants to do that, it would be interesting.